Hey guys, in this video we're going to have a look at symbol equations, one of the ways that we can represent chemical reactions. Now symbol equations are a bit trickier than the word equations that you might have seen in the previous video because they involve something that we call balancing. So chemical reactions need to be balanced when we're talking very specifically about the atoms that are involved. And in symbol equations, we are talking very specifically about the atoms that are involved because we show them very clearly. Just to illustrate that, let's write the word equation for the water splitting reaction once again. So water splits into hydrogen and oxygen. Let's write this out in terms of the chemical formulae. So symbol equations, we write them out in terms of their chemical formulae. So you need to know, with symbol equations, you need to know chemical formulae. You need to know chemical formulae of substances. So water, you probably know that water's chemical formulae is H2O. Okay? And hydrogen exists not as a single atom, but because hydrogen needs an extra electron inside a shell, you have to form, a covalent bond with another atom of hydrogen, and that creates H2. Oxygen forms double bonds with oxygen. An oxygen atom needs two extra electrons to complete that shell, so it forms two bonds with another oxygen atom, that gives you a stable oxygen atom. More on that in the covalent bonding videos if you want to go there. Anyway, here are the molecules of water, hydrogen, and oxygen. Now you'll note that that on the left side of the reaction, if we're going to count the number of atoms that we see, at this stage there are two hydrogen atoms. So if you look at this chemical formula, there's two hydrogen atoms and there's one oxygen atom. Okay, so on the reactant side, on the left side, we have two hydrogens and one oxygen. Let's say there's two hydrogens and one oxygen in a water molecule. They react. So water splits, It splits into hydrogen and oxygen. So on the right, at this stage, we have two hydrogens and two oxygens. So if that water molecule split into hydrogen and oxygen, how do we have an extra oxygen atom? How is it that we have one extra oxygen atom compared in the products compared to in the reactants? Now that can't be right. Okay, this cannot be right. So we have to fix this. And the way that chemists fix this is they put coefficients in front of the molecules. So it's probably sounding a bit like mathematics and algebra, and it's exactly that. To fix this problem of having too many atoms on one side, we just increase the number of atoms on the other side. So let's just increase the number of oxygens, because currently we have a shortage of oxygens on the left side. So we're going to put a big coefficient in front of this water molecule. I'm going to put a big 2. What has that done to the number of atoms? Let's count again. So now, what does this 2 mean? This 2 means that there are 2 water molecules now instead of just 1 before. And because there are 2 water molecules, we now have, instead of 2 hydrogens, we have 2 times 2 hydrogens, so we actually have 4 hydrogens. How many oxygens do we have now? We have 2 oxygens. Now these oxygens we find are now equal. These guys here are equal. So we're happy with that. But we've now unbalanced the hydrogens. Before they were balanced, like there were 2 hydrogens on the left side, 2 hydrogens on the right side. Now we've got 4 hydrogens on the left side and 2 on the right. So this cannot be right. This needs to be fixed as well. Well, that can be fixed by increasing the number of hydrogens on the other side. If we put a big 2, a big coefficient in front of the hydrogen molecule, does this fix things? Well, let's see. Well, there's still 4 hydrogen atoms on the left side because we haven't changed the number of water molecules on the left. But now there are 4 hydrogen molecules on the right as well, because a hydrogen molecule, there's 2 hydrogens usually, but we've got 2 of them, which means that overall we have 2 times 2 hydrogen atoms, which makes 4 in total. So we've also now balanced out the hydrogens on the left and the right. So now it makes more sense. So we've got two water molecules essentially splitting into two hydrogen molecules and one oxygen molecule. And this can be proven with experimental, proven in an experiment. If you were to split water and you were to observe the amount of gas that is produced, there's twice as much hydrogen that's produced compared to oxygen. This is a very standard experiment. There are videos all over YouTube for that. But it's really important to really get this idea that there must be the same number of atoms on the left as there are on the right. And we're talking every element must be equal in the number of atoms that go in and the number of atoms that go out. So for every hydrogen atom that goes in, it must come out. And for every oxygen atom that goes in, it must come out. Now you're probably wondering, why is it that I can't just change the number of atoms inside the molecules? So like, let's just write it up again. Water splits into hydrogen and oxygen. So the problem that we started off initially was that there were too many oxygens on the right side, or not enough oxygens on the left side. And a solution some people propose, and this seems like a logical solution, is to just increase the number of oxygens directly. So let's just change the subscript of oxygen there. Now, what's the problem with this? What's the problem with changing the subscripts? The problem is, well, is this still water? No, it's not water anymore because we've changed its chemical formulae altogether. This is a completely different substance. This is hydrogen peroxide, and it's no longer water. And that's the big thing with using coefficients instead. This is the main reason why we do use coefficients and not just change subscripts. When you change subscripts, you change the substance. If you use coefficients, you retain the original substance. You're just increasing the number of molecules of that substance, or increasing the number of atoms of that substance. Okay, so it's really important. We do not change, and I'm going to say ever. We do not ever change subscripts. To balance equations, we do not ever change subscripts. Let's be clear on that. All right, so make sure we are balancing chemical equations using coefficients. All right. Now I'm just going to put one more example. This is a combustion reaction. This is the methane. This is methane and oxygen reacts to form carbon dioxide and water. I'm going to write out the chemical formulae for this, and I want you to pause the video and have a go at balancing this chemical equation. All right, so you might see that in terms of the atoms involved, in terms of the atoms involved, we have a couple of imbalances. We have imbalances in the number of hydrogens and the number of oxygen. So to balance this, what does it look like? I'll just quickly go over it. That should balance things out. So after changing that, we should have 4 oxygens here. No, that can't be right. Oops, that should be a 3. So we should have 6 oxygens here. We've got 6 oxygens here. We now have, well, we still have 4 hydrogens here, but we have 4 hydrogens here and 1 carbon on both sides. And this is a balanced equation, okay? We have the same number of atoms going in, and then they rearrange themselves, and we get the same number of atoms coming out, rearranged. All right, so here's the video on writing simple equations. Hope this helped. Thanks for watching, guys.